All right. We will wrap up our root finding techniques today. So last time we introduced so-called open methods. And open methods are those that just take and iterate, like start iterating from a number. They're not requiring you to take a look at the function and find the bracket or anything of that sort. Okay? So that's the easy part about them. The hard part about them is that it doesn't always work. Okay? So first option that we have is a fixed point iteration. Fixed point iteration simply reformulates your function. So you're solving for f of x is equal to 0. For instance, there is an example here. This one we looked at, it's x to the 4 minus x minus 10 is equal to 0. I can rewrite that in two different ways so that it's in a form, equivalent form of x equal to some function of x. And I call that some function g. Okay? So there are two versions here. Okay? And then idea is that you give yourself a starting x, 0. Okay? And then you start iterating. Your x0 or x1 is 0. And then your x1 is that function g of x0. And you keep going like that. Okay? So in the next step, you update your x and you continue with finding your new x. And this is great when it works. We noted in class that basically in absolute value, g prime of x has to be less than 1 in order for this to work. Otherwise, you're going to diverge. Okay? So we exemplified that in class. Whoa. Okay. We exemplified that in class. So basically, for instance, this was we already noticed that this would be a good choice for g of x in that same problem because my g prime of x is going to be small. So, because my g prime is 1/4 x plus 10 to minus 3 over 4, right? So that's going to be small. So basically, the way I'm going to proceed is like I start with some x. I remember my previous estimate. I compute my new estimate. I can figure out what the error is based on the last two estimates. And I count steps. And this is it. Okay? This is the iteration. Do you need to compute g prime for this iteration? No. But if the iteration fails, then you can go back to g prime and figure out why. Okay? So if I execute this, and I'm starting here with 10, okay? I iterate here in 3, that's like really quickly, okay? And from 10, I get to x, so I can see my two last iterations are relatively close. I can make this stricter if I'd like. Let's do that, okay? So, well, then it's going to take 5 iterations. It's still not a lot of iterations, okay? And within the number of digits printed here, I can't even see the difference between these two iterates because my error is less than 10 to the minus 4. Okay. All right, so iteration is simple if it works. A more common method, and it's actually a faster one, is Newton-Raphson. Okay? So now I also start from some chosen x0 or x1, however you want to call this first equation. And then the next one I compute as xi minus f of xi divided by f prime of xi. So if I wanted to convert this code here to Newton-Raphson, so this is my fixed point. This is the whole point of reusing the code, cut, copy, paste, and then start from something you have. So basically the key difference is the way I'm computing the new estimate, right? So instead of g prime, okay, my new x will be something else. Following this formula, what will it be? X minus, or x old, works with x old because both of them are x at this point. So then f of x, what is my f? This is my f, okay? So it's x over 4, x to the 4 minus x minus 10. Divided by, what is my f prime of x? Come on, it's a polynomial. Thank you. 4 times x cubed. Minus 1. Yes? That's it. That's the difference. Okay? So let's see how fast that works. So I'm just gonna, I need to redo I is equal to 0. Okay? And I'm also going to say error is equal to 1. If I didn't do error is equal to 1, would the second loop I wrote in here ever execute? Because I would have a very small error at the end of fixed point iteration, right? So let's see how fast this one is. I could also simply say, so the way to turn off a code, you could comment it, or you could just say if 0 end. Okay? So if I do if 0, it's never going to execute. If 0 is never true. So I can just quickly turn it off and rerun. Okay? And in this particular case, turned out that this method is actually slower.
How did you use the other equation?
Huh?
There's the 2 different ways to solve for.
Newton-Raphson is always one and only.
Yeah,
Oh yeah, it matters. In fixed point matters a lot because the first one wouldn't converge at all. You would get infinity. Okay.
This one doesn't.
This one, so no. So out of these two options, okay, this one would not converge, period. Okay, so it matters a lot. Okay? And this one, and we tried that out, I think, 2 class periods ago, right? So I'm not even considering the first option, right? So this first option doesn't converge, and the second option converges.
But on your Newton-Raphson equation, you use.
No, Newton-Raphson is one and only. It's f of x, okay? It's not g. Okay? F is, well, it's not one and only. F of x you can rewrite in a different way, right? Because if x to the 4 minus x minus 10 is equal to 0, 2 times x to the 4 minus 2x minus 20 is equal to 0 as well. So those two are equivalent. Okay? All right. So in this case, I'm actually slower. It's actually hilarious that every time I claim, well, Newton-Raphson is actually much faster, and it seems to be that I'm always finding a case that is opposite of what I say. Yes? Always. You have to start from something. Otherwise, what are you going to do? So, and that's the part where it can be tricky because depending on where you start, you might have to start. And that's the hard part about solving for roots. Okay. Finally, so in this particular case, we had a polynomial, we had a given function. It was easy to find f prime. That might not always be the case. So there is a secant method that will basically replace f prime of xi with a finite difference form of it, right? So it's just going to take a slope of f at that point. Let me just quickly show. So you're going to actually have this here. So this is basically replacing f prime with f of xi minus 1 minus f of xi divided by x of xi minus 1 minus xi. How many starting or initial points do I have to have for this? 2. Okay. So I have to initialize this function with 2 starting points in order to actually have this approximate. But that's the only difference.
They both use a formula for those two.
You just, it's a formula. You start with 2. In this case, you start with 2 values, and you just evaluate what the next one is. Okay? So that's the easy part about these open methods. Okay? And actually, this false position, the secant method actually reminds very much of what we call false position. In false position, we found the bracket first, and then we called xu and xl my ends of the bracket. Okay? And I would keep finding like my new xr, and then figure out what my new bracket should be based on the values of f at xr, u, and xl. So what is basically you just keep finding your bracket. And formula, if you look at this, if you equate xl with xi minus 1, xu, xi, you're getting the same formula. Key difference is that secant method just starts with any 2 values, keeps going. And in false position, you actually have to make sure that xu and xl are a bracket, meaning that function f has opposite sign f for f of xu and f of xl. But formally, they look the same. Okay? And in theory, for most cases, bisection, so when you plot your error, bisection will be the slowest, then false position, then secant, then Newton-Raphson. And somehow fixed point did not make it to this analysis. Okay? But that's just in general, every different case is slightly different. All right. Finally, there's one more modification, and we could keep going on and on. A lot of these functions, a lot of these methods, they don't always, there's no method that works all the time. So that's why we need to have a lot of options. There's one more option is to, in order to evaluate f prime, this is, you just evaluate f of xk plus some small value d minus f of xi divided by d, instead of giving it to different points as options. It's just an approximation to f prime, so that's a modified secant method. So this pretty much is it. Okay? The only one more comment that I want to make is that when you're using these methods, you're finding one root at a time. Okay? If you have multiple roots, okay? Multiple roots, by that I mean, for instance, if you had function f of x that is x minus 1 times x minus 1, so 1 is double root times x minus 3. Okay. You will typically find one at a time. The problem in using these methods is that often when you have a double root, okay, then it's going to, for instance, be hard to find the bracket, because double root causes this parabolic behavior. You're both a root and the local maximum at the same time. Okay? So basically f prime at that point will be a 0. And you can see in Newton method how having f prime as 0 can cause issues. Right? So there are certain numerical issues that you can expect with dividing by 0. So bracketing methods will not necessarily work for double roots, will not work for double roots, period, because it's going to be hard to find the bracket because both of these values are negative. Okay? So you have to have some knowledge or suspect that you might have a multiple root and then find that first. And you basically both f of x and f prime of x. So you might want to find roots of f prime first, okay? And see if some of those roots is also a root for f of x in order to get that out of the equation. Okay. All right. And there's some alternative formula. I'm not going to press on this formula. Again, we could keep going and amending these methods. Polynomials in themselves are a whole separate study, and there are methods that are specializing just for polynomials. We're not going to go in details. The key point is that what you need to know about basics of root finding, you have found out already. Okay? And if you want to check out some Matlab built-in functions, f0 is basically, you can define an M file, or sometimes an inline, you can define an inline function. And basically, you can then give it your initial guess. Initial guess is mandatory. And roots function specializes for polynomials. So how would I, using roots, how would I find roots of function f that we looked at here? So it's x to the 4 minus x minus 10. What would I type in? Roots of? How do I describe polynomial? By coefficients. So my first one is the one next to x to the 4, 1. X to the cube, 0. X to the square, 0. Minus 1, minus 10. Correct? Do we remember how to represent polynomials? All right. Oops, roots. Oh. So this is close to 0 times I. So this is the one that we were able to find. So this is very close to a real number here. And then there is a... All right. So in review, roots of nonlinear equations show up a lot in applications. You will see them all over the place, especially in your thermodynamics class. We learned some different methods. None of them is perfect. Bracketed methods, they kind of guarantee that you're going to converge, but you have to do some graphical exploration of your function first and find the so-called bracket where the function changes sign in that interval. And those two methods that we mentioned are bisection and false position. Open methods, they don't have guaranteed convergence, but they're easier to use. You start with some sort of initial guess and you keep going. Okay. Fixed point iteration, Newton's and secant method, all of them are literally a one line of proper code where you actually put how to find your next iteration, and given a starting guess, it's a very easy thing to program, but again, there's no guarantee for convergence. And different functions will give you different, very different behavior in terms of how fast do you converge, if at all. All right, that basically ends our lecture on root finding. I have 3 minutes left in the class, so I will not start the new lecture. We will start with systems of linear equations on Wednesday.